So we will talk about challenges in both domains, integration and the visual discovery as a way to do this. Okay, I want to start with history. Everybody knows that the term AI, McCarthy actually coined in 1956, and in 2006 the celebration of years of AI. Of course, it was a strange celebration because by that 50 years we did not have much celebrate. And the conference was at Stanford and in 2006, and John McCarthy was alive that time. Obviously, he was asked about the results of the first 50 years, and was a small sub-symposium under the name "What Went Wrong in AI." Okay, why did those promises not realize it for the first 50 years? McCarthy told us that 50 years too short and much more years are needed. And it was, as you see, exactly 20 years before. Now everybody knows about AI progress, but AI progress now in completely different approach in comparison what McCarthy wanted. He even mentioned neural networks as a bad idea. But today, AI all is based on neural networks, as you're well aware. Okay. So now the question is today, what went right with current AI network? What is failing now? Okay, obviously accuracy is here. More for many tasks, but the time, 51st years, situation was opposite. Explanations were available because methods were really interpretable, but accuracy was not here. Now we have accuracy, but we don't have explanations. Okay, and so that's the situation. Okay, why we need explanations for today models more than in the previous 50 years? The answer is quite simple. If you see the examples, you see that Panda was converted to Gibbon with for humans nothing changed, but for automatic method adding this small adversarial noise changed the classification. And of course the system recognized these eggs as a ping pong balls. It's also not what we want to do. And of course this is a kind of exotic examples, but all of us are aware about hallucinations from large language models. One small example which I just experienced recently. I asked a large language model to summarize particular topic with new publications and provide references. Okay, they did it in the matter of seconds. Then I analyzed those references, and Google Scholar did not find any of these references. So then you may ask how. So you need to ask large language model, can you actually explain how do you use such useless results? Of course, you don't need to ask this in such aggressive form, but the essence is the following. You may get an answer that they used parts of the sentences, combine them, printing next one, and this is how they provided references. Okay, so what it means? If you will translate it to the level common for the normal user who does not know anything about tokens and prediction of them, basically you will just learn that they pick up, let's say, and from one reference it's its title, and its author, and combine them because they are obviously quite related because all of these references to the same topic. Okay, when you get such explanation, you basically tell, I understand it, but I don't want to use it. I want you to build a system. So explanation actually help us to stop using system and request to make more sophisticated system. And I'm pretty sure that developers of language model most likely the number of such hallucinations is decreasing. But fundamentally, it requires explanations. Okay, now where we are now with the current situation with explanations of AI models. Okay. We have this one, white box versus the black boxes. In black boxes, explanation is present. And ideally, domain expert should be able to understand and accept it. And for the black box models, we don't have explanation for they are not sufficient for the domain expert to accept. Okay, so now what is the main point in the first category? So we have a non-explainable model. Maybe it's red, not very visible. So it's a common really large language models and most other of neural network models are not explainable. Okay, so what it means? Domain expert does not understand the model. Then we have explainable models. We have some existence. It means that domain understands either model directly if it's already explainable or can understand explanation of the black box. Then we can actually see explained models. Often people do not distinguish between them, but it's really very important. So in the explained models, domain expert actually accepts explanation. For example, in my example with references, I obviously accept that explanation as a basis to use the model because I understand. So I definitely understand that explanation, and I'm not happy with model, not in explanation itself. Okay, and then, so that's difference, unfortunately, not very recognizable, and it's very rare that the models are really. It means the main expert tells actually understand and accept it. Actually, there was a review of multiple models, explanation models. People listed in those surveys of publications, and only literally a few of them really asked domain experts, are they accepting those explanations or not? It means most models, even being explainable, not explained. And then next category, models, where domain expert is ready to deploy the model. And this is a completely full story. Okay, now you can see, and this is very rare. Let me give one recent example here in Seattle. As you know, the mammoth, it is a yearly test which insurance companies pay. Yes, so that's well known. But once I actually lady came to for yearly mammography, and they told you that she needs to pay extra $40. I asked what for. That they will give extra recommendation for your mammography test. It's on the AI model. But then the question immediately came: why insurance? Okay, investigation actually FDA did not approve it. FDA did not object that you can get second opinion if you want to pay. Yeah, so it means that actually domain expert at the level of FDA as a real competitor to the radiologist. So now you understand all scope of this different levels of the models which we need to deal. So we have a tremendous number of issues that need to be resolved to really move to the last ones. typically people assume that for high-risk models like mammography or cancer, it is really need to have a model. But I gave you with my own experience with references. It's definitely not high risk. Yes, so I can go to Google Scholar and check all references which are right or not. And even if I make error, it's no big deal. Okay, now you can see the technique designed for explanation and providing AI models. You can see that it's quite large number, 20.5, so recent one, and actually this one on the left actually, and it's interactive, so you can click to any of these visuals and can see them in detail. Oh, and actually even searchable. Okay, so and here you can see the typical example of such visualization. If you take a close look, you will see that it is a combination of several well-known types of visualization. Something like bar charts, histograms, scatter plots, and even parallel coordinates here at the bottom. Okay. So, and this table also has a list of methods which have been used for this one. And you may notice that practically it's old methods which have been developed in visualization by visualization community for decades, not related to AI at all. So, and for what's the specifics of the AI? In the AI, fundamentally, we deal with multidimensional data. But most of those visualizations, please, it's probably too small for you to read, it's here, are one-dimensional. But you understand that one-dimensional data do not represent fully the story. But the problem is actually twofold, and we will talk about so typical today's systems are working this way. They build some kind of analytical explanation, and then they visualize that explanation with the bar charts, or like I shown you in the previous slide. So visualization of explanation, it is not really a visual explanation. Later on, I will give more example explaining why visual explanation is much more interesting and needed. Okay. So now I summarize my overview. Now we have an existing machine learning method and existing visualization method, and we try to combine them. But it's a classical situation from Maslow that if you have a hammer, that everything is screw. Yes. So, of course, if it's screw, then you will have results from this picture. But you really need a nail. Okay, so we really need to develop both AI methods and visualization, which will be really what I call them native integrations. So that they, and what practically, it means that we need, first of all, be able to visualize multidimensional data so that human can actually see them and understand. But humans have significant limitations. How many data we can remember, and so our capabilities. So it is not trivial situations. Okay. So and we need so-called lossless visualization method, because if you have 100-dimensional data, then there is a good chance you lost baby. So you need to preserve your data. Okay, so this is how lossless interpretable visualization come to the play for high-dimensional data, and we will talk about it. And another major idea is full interpretable high-dimensional machine learning in 2 dimensions, because normally we have a multidimensional. Is in large language models, we really talk about millions. In typical medical tasks, they talk about a couple of 10 attributes of a particular disease which they need to analyze. So it's not necessarily always millions, but it's definitely a large number of attributes. And if we will be able to visualize those in 2D, then humans understand it, especially domain experts who. So it will, and I will show that it's actually doable. Okay. So now hopefully it's clear that integration includes analysis of high-dimensional vision, in predictive models to deploy models, and include interpretability, scalability, and cognitive augmentation to our human limitations. Okay, this is one of the types of pipeline that can actually work. We have a first rough part, which is a problem specification, and the second one is a modeling. And in the modeling, you can see component which does not exist in standard AI modeling procedure. Actually, interactive model discovery in 2D space visualization, and on the right, it's traditional machine learning, what is called AutoML. You build models, and then you can again do visuals on the top of it, basically doing visual learning of those models. And I will show you examples how we can help justify model good or bad. Okay, so and on the left part, where the problem specification, you really try first visualize data as much as possible and augment data to see. So, and here where domain experts actually can do much of the work. And because we are very limited in abilities to represent multidimensional data, we in essence live in three-dimensional world. Even 4 dimensions, it's a challenge. But so, and the standard Cartesian coordinate system, which 400 does not allow us to do that. So now you can see solving these two things and allow to realize that idea. And this is actually partially okay. Now it's about visualization of models and prediction from actual discovering models visually. Now you see on the right, this is a proof of Pythagorean theorem. Sanskrit, but in English translation, still one word, see. Okay, I have seen, and for me, it's required to write extra lines and modify slightly the picture so to be able to prove that it's really true. So now you see, in 600 BC, they were so this is a really visual reasoning. And of course, classical geometry from Greeks is also practically all visual reasoning. Okay, now I want to be much where you have 15 points, two-dimensional, two classes. And so they asked you, please build a classifier. What people start? They will try to build linear classifier. So if ax plus bx is less than some threshold, then it's a class 1, another threshold is class 2. Okay? But for this particular data, you may actually see any possible line here. You spend time and money to build such models. You immediately recognize which one is actually need 2 lines, red and blue. Because you need to find parameters conceptually. So what it means that visual discovery, you actually discover a type of photo. And then you put computing to identify parameters. So that means we humans can actually be with some system. One, define parameters, but you can discover. Okay, but now we go to real data. So this data multidimensional. So it's 18 dimensions and 20 scales. And we obviously cannot do the same picture like we did with 2D, yes? With simple reason. We are not able to do this. So we need actually what I call ND glasses, like a telescope or microscope, which were developed. So if we will have it, you know how much progress a microscope did. So the only issue is to build such ND glasses. Of course, this dog is starting it. Okay. Now I want to provide examples of actual situations. This is a 9-dimensional data. Basically, it's breast cancer data. And they are represented in 2 dimensions with standard methods of visualization data, multidimensional scaling, principal component analysis, Fisher discriminant analysis, and support vector. You see all of them different, yes? Okay, and they will separate both classes because this is unsupervised learning, so it's not, you cannot expect. But the major problem, even not that they're not well separate these two, the major issue is the meaning. They are artificial, and basically domain expert does not have a natural meaning to assign them. So it means that only, say, a person without much responsibility will try to use models based on this visualization in practice. But it's illustrate positive part also that if you will be able to present multidimensional data in such 2D way, where you have understandable access and some and meaningful this one, then it will be ideal situation for humans to be convinced. Okay, now I will tell you what options we have. So one option which I just illustrated, and look them to two-dimensional data. Like mouse is not visible, yeah, so you don't see my mouse. Yeah, sorry, yeah. So basically, it's on the top right. You have multiple dimension data and you visualize exactly like I shown you in 2D. Alternative way, you discover n-dimensional pattern in lossless 2-dimensional visualization space. So it means that it fully represents ND data. And for this one, you cannot use points. We will use graph. I will have enough time because. And then, obviously, the second approach, unfortunately, we as humans cannot, even if we will be able to show it, we will not be able to analyze it. So we would need really two things, lossy and lossless. So it should be happy marriage. Of course, it is still in the process and there are not many examples. Okay, now another example illustrating what human can do better than pure automated system. And so it means integration of human abilities and computer can be produce good results. Okay, so you can see famous Fisher data iris and pictures of 3 types of iris flowers. And below it's a linguistic description how this looks like for humans who can take a look and say, okay, first one is small and small widths. Okay, and then in visualization, you can see here the of first class, second class, and third class. And you can see done quite well. Only 5 errors. Okay. Then you can see this is a linear classifier. Second one is support vector machine in the middle. It's also quite good. 5 errors. And then you have decision tree. It's even better. 3 errors. And you can see they actually produce very different areas, yes? Okay. So which one you will accept? Of course, if the new cases will come exactly which are available, then but if you come like red stars here, then you may notice that it will be recognized here, but not necessarily will be recognized with 2 others. Yes. So now you can see the issue, but we actually have human description that's small widths. So it means that it's really need to be somewhere here. It should not go there. And for that one, definitely should not go there. So we as a humans able to define it and tell actually do overgeneralization. That's a straightforward result. And by the way, the method which we developed, actually briefly illustrated here, it allows to see and circles. You can see circles on the right on the top. It shows. Okay. So and now there is a mathematical result, theoretical limits, how we can preserve NZ properties of two-dimensional space. Actually, in the Charles in 1984, and it looks actually great. So it basically, I put it probably here. Basically, it tells you how you can estimate the error you will get going to the low dimensional space from the high dimensional space. Okay, so it looks that you can control it. So, and people often consider this is a good example, but later on in 2003, other people actually made conclusions out of it. Data, and the result was following. For 10 arbitrary high-dimensional points, you need 1900 so-called low dimensions to preserve. It means for 2D or 3-dimensional visualization, it's completely impossible to preserve data. So we really can only hope that our smaller dimensional data so that they can become dimensions. Okay, so now I'm going to what I call general line coordinates concept. Okay. First of all, I have about probably 20 minutes. Okay, let me see. So, you can parallel coordinates. What's the idea of the parallel coordinates? You have 4-dimensional data. You have a first attribute, second attribute, and fourth. So instead of putting them orthogonally like we do normally, you put them parallel. So, and then what you do, you put a value on the first one, on the top, around 4 points. Then the line going somewhere around 3 in the second attribute. Then it's go around 2 in the third one, and around 2 also in the fourth one. Dimensional. Yeah. So without loss information, you can restore it. Okay. So, and Alfred Inselberg actually developed them, and then people actually discovered that it was also discovered in the 19th century, but Inselberg actually made it mathematical and really well known to people. And few personal stories, because I invited him to Seattle, and he kind of encouraged people to work on the topic. Unfortunately, he passed away. Okay, now you can see not only parallel coordinates but other what is called shifted coordinates. So what you have here first is a pair of standard coordinates in the second pair x3, and you put exactly the same data in this form. So first one is a point in one, point in other one, and you connect them. So this is called shifted paired coordinates. But on the last picture, on the right, the same idea. And now you can see this picture looks much better. So red area completely separated, green and blue are partially separated. So you have much better way to analyze, but all of them represent the for human analysis, they are very different. Yes, so that's benefit of using them. Of course, you may ask how to do this. Of course, it requires remediation. So the tools are available, but for your personal data, it's need to experimenting. Okay, there's another option with the same data. Instead of considering parallel coordinates, we actually turn some coordinates on the angle. And the line which was a blue line on the top is a blue line in the middle. And then what you do, the yellow parts up below this blue line, you actually stack them on the top of each other. What you see here, and then every line from here you represent, and you get a picture. It is much more cleaner and explainable for analysis than the previous one. So this is an illustration that we can actually work with four-dimensional data without loss of information. 3D. Okay, this is another example. You actually can put your coordinates initiated from the single center, like you see on the right. And you connect all values similar to parallel coordinates on all of them and get kind of star. Okay. This can be done not with 7 attributes like here, but 170 dimensional data. And it's actual data class of mask chemicals and another one class of non-mask chemicals. And you as a human able dimensionality. So it tells that we as a humans can actually operate with this. Okay, that's another example how we can present dimensional data into analysis. Here next to me, it's actually cancer data, different breast cancer data. Red, it's a malignant cases, and blue, yellow, it is a benign. And you can notice that it doesn't allow you to see pattern here. However, on the right, it's the same data, visualized in a different form, which is called basically using property of monotone Boolean functions. And actually, the malignant classes actually black one and white ones are really it is it's a benign cases. And it shows full 10-dimensional binary space. So now you can see that again, what I claim that doable. Of course, it requires a lot of extra work, but this demonstration shows that it's doable. Okay, now what is the general line coordinate? Yeah, I still give you examples, but did not give you the finish. So we have coordinates where coordinates actually under angles. You can put arbitrary angles, or you can put even some coordinates like here on the top, horizontal one. Or you can put all coordinates on the line and use curves to connect points. So you can see that variability of possibilities to put coordinates in this. Okay, and now practical, because first it looks a kind of mathematical exercise, nice but not useful. Okay, now you can see what we can do. I already shown you example with parallel coordinates where actually coordinates are having angles. Okay, now we start to control those angles, not just arbitrary angles. So let's assume we have a four-dimensional 1.2, 1, and point 8. So what we do? We put point 8 here, point 1.2 here, 1 here, and 0.8 here. Okay, so, and then we stack them one on the top of the another. Then we project it here. If you see on that picture here, several lines are actually projected. From one projected here, from another class projected here. Okay, so this is the idea. Then you actually start to optimize those. And where you have a benign environment, where you actually able to classify with accuracy 98 whatever percent there. So what it, in fact, this is mathematical proof that it's actually linear to classify any loss of information. All four-dimensional information is presented here. Moreover, because it's interactive, you as a user can move this green line and you will change accuracy. That's it's basically a threshold line. You can see projections. And of course, there are misclassifications. So definitely, two red cases are misclassified. You can, if you're more concerned to preserve practice, you can move green line, but the price will be that you will increase. But typically, in cancer study, people are concerned about malignancy. They can ready to do extra test with benign cases. So, and this is called general line coordinate linear, GLCL. Okay. But now you can see that it's quite but because it's cases, they are really not distinguishable well. Of course, you can pick up any one, you see them. So the alternative way is that you make a picture like 0, 1. So you create in this case 700 images because that's about number of the. And this is actually what was done. So this is a fragment of those images, and those images put to the functional neural network, which was able to this data with accuracy 97.22%. Even data images were compressed; they are not images. So now you can see that there are multiple opportunities to build. Of course, this is a nice property that computer didn't work. But of course, after that, you need to interpret this one how. But fundamentally, options are here. Okay, and there's other zero line infinite. So what is there? You can circle. So segments. So you can call so that rectangle actually represents four-dimensional data. Then pentagons, you can triangles, even quadricle, and put all possible ways to develop those coordinates. Even frame, which is typically used in engineering, have an every point that dimensional space, they typically analyze it, and so each of them will create several general line coordinates. Okay, so obviously I don't have time. I just one of the short list of general line coordinates and similar 3D. Okay, then I want to illustrate you another shifted coordinates. I already gave you general idea, but this is a really useful example. What you see on the right? You have a two blood pressure attributes, cholesterol, and some other. Okay, and pulse. Yeah. So total four attributes. And now you can how it is done. This coordinate pair of coordinates are shifted relative to each other. So that desirable value became as a single green point. Because if you project this point, so the shift was organized that way. Oh, okay. Arrows. And so if that green is your goal point, you want that patient gets position, then you can see from that red position, it's smoothly moving to this green. Present exactly the same data, but much less convincing here. So that shows that for particular data, you can actually there is a program which is able to compute how much shift should be done so the desired 4-dimensional converted to single point. Okay, now you can see there are even more ways to do general line coordinates. What is important here? You are representing n-dimensional data, but only using not n points, but using half of the points. The idea is the following. What you do here, you have one coordinate system here, second coordinate here system, and third coordinate here. 2 points go here, 2 points here, 2 points here. This triangle actually visualizes six-dimensional data. So, and of course, similar with ellipsoid. Okay. So now I of course don't have much time, but I get the idea. We are combining somehow vectors, and this is a 6 different methods to combine vectors to get those general line coordinates. Of course, there are statements that for some general line coordinates, you can have half of the number of points relative to standard one, like parallel coordinates. Yeah, I already shown you the idea here with this three. Okay, then another example with collocated coordinates. You see, in shifted, we have one pair shifted to another, like we have seen with blood pressure and pulse. But now we have a full actual data of the hunger index from United Nations. And this is a standard. On the right, it's a standard visualization with graphs, basically 4 time periods, and you can see them all converted. They became much without overlap. Again, can be analyzed. So basically, what it means, let's say orange pair, orange arrow. So the bottom of that arrow, it means that the first two data skip the second two. And you can see if progress is going, if it's go up or down, you can see how progress is actually going. Okay. And now I have actually just 4 minutes left. So I will give a few more examples and we go to conclusion. Okay, this is a very important example. Challenger knows about this. Okay, and this is on the top 2 visualizations of a Challenger disaster standard visualizations. But on the bottom, it's a visualization of the same data using collocated pair of coordinates, one pair of coordinates here, x1, x3, and x2, x4 here. And now you can see immediately that one line goes up, or two lines horizontal, and other go up. Very similar to situation when the actual Challenger disaster actually happened. So if they would have that visualization, they maybe would be more convinced than analyzing those ones where it's not easy to keep. I want to not go to details, but focus you on really software which we developed. One of them it's JLC principle. So we actually try to explain first pair of principal components, second pair, and this idea of GLCL. So you can see impact of you click on the point and you can see how it is actually by original attributes from principal components. Okay, then there is examples of 3D examples with glyphs. So you represent pictures. So, for example, malignant cases. Okay. So then another topic important how visuals can help in machine learning is the estimating accuracy, because we told that today's methods are accurate. True and not. Let's see what's happened with this cancer data. You can see all standard machine learning methods from decision tree to multilinear perceptron give over 95%. Good. Then what we did on the right actually this data for testing, and you can see how dramatically dropped accuracy. So, and if the first one, KNN was the best one, but here, actually, naive wise was much better. So, and allowed to find worst cases. Basically, we were able to visualize data and boundaries where the mix needs to capture and grab them and put them to the test. Okay. So this already and it allows us to analyze again worst case. So you can pick up data and get worst case, which was 98, which I presented you before. Okay. So software implementation, it's my lab, this other lab, and then we have partners in industry when we have a project for them, and there is our collaborators in Argentina. Okay, this is the students who worked, and then there is a which visualize decision tree. So you can almost n-dimensional data see visualize it. Again, it was used shifted paired coordinates. Okay, and this is a concept, but this is the same dimensional data from this, and you can see how decision tree clearly all cases are showing this slide and each slide. So user can see each individual case. Okay, there are more examples. So this is a type of software. I just show you what we actually did. Okay. So the Boolean stuff, it's illustrate how it was actually built. Of course, we don't have time to talk. I illustrate you. Okay, so now summary. We need native integration tools. And I showed that native integration tools can be actually designed. I give you example that it's doable. Okay, and we need full 2D machine learning. It's also, there are examples where it can be done. Okay, and future, obviously, moving from that red position today to blue position. That's the whole area of development. That's basically it. Okay, future, I already told you where it is. In one context, let me emphasize. So the idea is, of course, it's kind of future, that the domain experts who are not data scientists will be able to build models themselves. So this way they will trust the models because they built it themselves. Okay, that's basically it.